Okay, folks, let's get a start on the next topic. How many did you get done then?
Almost finished.
Really? Fantastic. Yeah. Diego?
4. Well, 4, I mean 3, because number 3 was on top.
So then I want you to say the resistance of whatever. You take it from the linear part.
Usually, yeah. Depends on the question, but yeah. If they just ask you to plot it, you know. Alright, we'll continue. Capacitance and capacitors. Yeah. Got that? Yeah. Okay. Yeah, it's not too difficult. Okay. So if we look at the following circuit, it's extremely simple circuit, very, very simple. You've got a power supply, and you've got two metal plates, two conductive plates, doesn't matter, copper, whatever. And between the two plates you have what's called a dielectric, but I mean, I think this still works even if it's a vacuum, but the idea is you have two plates which are close together, but they don't touch, okay? And something interesting happens here. If you turn this battery on, what will happen is this plate will become positively charged, and this plate will become negatively charged. And if you remove this battery, if you take it out, then a current will start to flow, but only for a short time. So, I don't know, like, it's like, I suppose I could use this, couldn't I? No, I can't. Okay, whatever. So the two plates are close together, but they don't touch. And then this plate becomes positive and this plate becomes negative. And then when you remove the battery, the cell, then this will start to lose its positive charge and this will start to lose its negative charge, and a current will flow out of it, but only for a short time. Okay? And this is a capacitor. A capacitor holds a small charge for a small time, and then when there's no longer a power supply, then the current flows out of it. Okay, so you don't need to draw this. Well, actually, I don't know. Do you have this? Is the symbol for capacitor? Did I give you that earlier? No, probably because it wasn't coming up yet. So you can add that to your notes. The capacitor symbol. Yeah. Okay, so yeah.
The way it says dielectric, is an insulator between them? You wouldn't want it to spark.
I think it's some type of insulator, because I think you get the same effect even with a vacuum. So I don't know, Zach, perhaps the material put between the plates can affect how well of a charge it can hold, you know. The construction of the capacitor is not really important for this course. What's the definition of a capacitor? So what would you say it is in your words? What do you think, Dorian? No, let's pick on Harry. I'm always picking on the front row. Let's pick on the back row. Harry, if you were to put this in your own words, what would you say a capacitor is? Give it a try. I'm not grading you on your English, don't worry. I just want you to try. If you were to say in your own words what a capacitor is. Oh. No? Don't want to? Okay. Who will I pick on? I'll pick on Gina. Gina, in your words, what would you say a capacitor is?
I'm not sure. Maybe it is something can store the charge.
Good. I like it. I like it. So maybe let's change your definition a little bit. So we need a better word than something. A device sounds nice, doesn't it? And it can store what? A small charge. Yeah. Okay, so let's see what I wrote. A capacitor, now you don't need to write this down. The old name for a capacitor was condenser, but that's not important.
Did it condense like the thing it had?
No, I forget. I need to delete this. Just forget you saw this. Is an electronic device that stores electric energy. See? Nearly got it, Gina. In fact, I'd say it's fine.
How is it different from a cell?
How is it different from a cell? Who can tell me?
So
A cell can
it
hold
can
current
store-
for a long amount of time.
Yeah, well, the difference is,
it produces.
yeah, a cell actually, through a chemical process like electrolysis, produces the current, whereas the capacitor first needs to take a current in and store it. So, I don't know, what would be a comparable example? Is there any other example in physics that's a little bit like this?
So a capacitor is a cell, but a cell.
No. A capacitor isn't producing current. It's only releasing the current it got earlier.
Like I'm not.
It's a freeloader.
Yeah, other way around. So a cell is a capacitor,
No,
but a capacitor.
No,
Why?
no, they're two different things. They're two different.
So a capacitor is like I'm
The
not.
cells can store
Just-
energy.
No, cells don't store energy. They produce it through electrolysis, through a chemical reaction. They're not storing the charge. It's not like
So what the battery is made up of cells that stores energy.
But it's also
No,
still
you keep saying store. I'm trying to correct you. A
Okay,
cell does not
produces.
store energy, it produces energy
Yeah.
through a chemical reaction. The difference is between, you could work and earn your money, or you can just spend the money that someone gave you. Do you know? So the cell is producing the current through a chemical reaction. It's not like the capacitor. The capacitor is only releasing what it's temporarily holding because a current passed through it. If I pass no current through the capacitor, then the capacitor does nothing. Whereas with a cell, I connect it up, produces current straight away. Yeah? No, you don't look happy with this,
No,
but you still don't look happy with it. I appreciate you understand, but you look unhappy with it.
I just don't know why a cell can't store energy, because you plug things in to charge them.
Yeah, but you're not, you see, it's a technicality. When you charge up your battery, you're not storing the charge. What you're doing is you're reversing a chemical process on the inside, which will later produce the energy. You see, here I'm using store in a very particular way, okay? It's the difference between,
Converting.
yeah, well, for
energy
example,
to electricity.
you could harvest some crop and put it in a barn, and you're storing the crop for later consumption, right? Would you say that the field that's growing the crop is storing the crop?
Technically,
No. You don't say the field that's growing the crop is storing the crop, right? It's producing the
yeah,
crop,
it's
right?
producing it.
And suppose you harvest that crop and then you replant the seeds. Are you saying, oh, I'm replanting the seed, so I'm storing crops for later. Would you say that? So I'm being very technical with the word store. I'm using store to mean releasing the exact current that came in earlier and you're holding on to it. Yeah? It's very particular with the English here. Yes. Any better? You still don't look happy with it. Oh, okay. Right, continuing. So we need to we need a way to measure how much or how big our capacitor is, you know, because some capacitors can hold a lot of charge, some can only hold a little charge. Oh dear. Oh, I don't want to be here. Right, okay. Oh, I just want to be at home. Okay.
Are you getting sick as well, sir?
I've been sick for about 2 weeks, but my poor students need me. Right, okay, what was I saying? Oh yeah, so some capacitors can hold a lot of charge, some capacitors can only hold a little charge. We need a way to measure how much a capacitor can hold. So that's the meaning of the word capacitance. It's how much charge the capacitor can hold. It's the ability to store electric charge. A common device to do such a thing is a capacitor. The unit for capacitance is called the farad. F, the symbol. Yes, sorry, I didn't write the symbol down. Mathematically, does anyone know what capacitance is defined as? Yeah, what's the formula to define capacitance? Mathematically, it's...
Which units has it?
Oh, I'm telling you. No.
Charge.
Yes, charge per watt.
Kilowatt hour?
Nah. Nice try.
What's kilowatt?
It's charge per volt. That's how we measure a capacitor's ability to store charge. We measure how much charge it can hold per volt across it. C is capacitance, Q is charge, V is the voltage. 1 farad, therefore, is the same as 1 coulomb per 1 volt. That is as follows.
Symbol is F. Just F or FA?
Just F.
Just F.
It's definitely not going to be Fahrenheit.
Oh, it's Fahrenheit FA.
No, I thought you were saying, because the only reason you use a second letter is if it could be confused with another unit.
Yeah.
But there's no other unit except for Fahrenheit that might use an F, which is forbidden in this classroom.
All freedom units of that.
I like it, freedom units, yeah. What's the temperature outside? It's 80 freedom units. Yeah, nice. Okay. Okie dokie. We got that? Yeah? Yeah? Continue?
Mhm.
Yeah? Okay. Now, here's an example, although a bit dated. Here's an example of a capacitor. So when you hit the button, you have to wait. The capacitor is charging up. And then it suddenly releases the energy. So capacitors are good as a device for producing a sudden surge of current. Now the circuit here would be quite simple. Let me sketch it for you. So you would have a battery, And then the battery is charging up a capacitor, right? And there's a switch here. Sorry about that. That's a switch that you can swing, you see. Okay. So right now, the current flows along, and then this becomes charged, and so it holds a large charge Q. Then what you do, this button, it swings down. So later then this guy swings down. So it's now connected here instead of here. You swing it down. No, I've done something wrong here. That's not what I want. Sorry. Oh, sorry, it's the other way around, isn't it? Yeah, it's here, and then you swing it down. So now it's here. Now it's right. Yeah, it swings down. So when you swing the switch down, it's like this is removed, isn't it? And which way will the current flow? So this Q now starts to release in the same direction. So this Q suddenly releases like nearly at once. And then this gives a large surge of energy to the bulb, makes the flash down. Okay, so this is a very simple circuit for how you could use a capacitor to build up, and then release. Yeah. Can we think of another example where a capacitor would be useful?
I was thinking like a computer or something.
The time frame is a bit too short to be useful as a backup. For a backup, you would need like a battery pack to switch to or something.
So on when you draw a cell, the big side is
The positive, yeah. Did you have an example, Diego? You have one. Let's see what Diego's one is, and
Yeah,
I'll
I was
get yours.
thinking like a computer somewhere, like for something if you have a shortcut, or no, not a shortcut, like the power drops or something, that the whole system doesn't end up with.
Capacitors are good for trying to keep the energy levels balanced. So in your computer, if you suddenly got extra energy, this could charge up a capacitor, and then if there was a dip later, then it could release from it. So you're right, capacitors could be used to smooth out energy. Your example, Lynn? Taser, excellent, yes. Taser is a good one, yeah. You all know taser? I was thinking of another example which is like a taser, which I thought maybe someone would get. Like a taser, except it's used for good instead of evil.
I think that's something, one of those things that you can,
Huh? What things?
I don't know, like you can set on fire, you know.
No, used for good instead of evil.
No, but you can use that on, when you go camping.
Now, I think Gina might know, but she's looking up the dictionary. No? No, okay. Come on. Like the taser, except for good instead of evil.
Good as in good.
Good. Save a life.
Oh,
There you go. Yeah, there you go. All right. This is another example of a capacitor in action. Okay. So you can hear the capacitor charging. Exactly. Yes, that's it. Yeah. Okay. Good. Right. Here's a small calculation example for you to do. I made up ridiculous numbers, I realised afterwards. My camera has a voltage of 380, which is like some heck of a camera. Anyways, it doesn't matter. I want you to calculate how much charge is held using the formula. Yeah, Q equals CV. Now just be careful, that's microfarads.
Yeah.
Minus 6. You get it? 0.57 coulombs? Yeah? Did you have that? Guys, yeah? Okay. Now, some rules regarding capacitors. So, when you have your capacitors in parallel, which way is parallel? Which way is parallel? One here and one here. Parallel, okay? The formula is like this. The total capacitance is like this. So, for example, if you had one capacitor here, yeah, and one capacitor here like this, the total is quite simply C1 plus C2. Fine? Yeah?
Different to voltage.
Yeah, it's actually almost opposite, isn't it? Okay. And remember, the voltage, same or different if they're in parallel?
Voltage is
Same.
The same. Remember that. Voltage is still the same. You don't have to write that down. That's from the last lesson. Okay? So go on. Have a guess. What do you think is the formula if the capacitors are in series? I'll go on. Thank you, Gina. 1 over C equals 1 over C1 plus 1 over C2. Oh, before we do that,
same as resistors.
I just need to say, I just need to say something about the Q. The Q also adds. Q is equal Q1 plus Q2. Okay. Now, series. So, Gina's correct. 1 over C equals 1 over C1 plus 1 over C2. That's if they're like this. Okay? Fine.
How did that even work? Capacitors were in series.
I used to do the proof. The proof's a little bit messy, and
Because it like releases.
And then the other holds in what?
yeah, the proof's a little bit messy because one plate feeds into the next plate. So actually what you really care about is only the very first plate and the very last plate, nearly. Okay. What about the voltage? Same or different?
Split.
Different, yeah. But they add still, right? The total voltage over the two capacitors is V1 plus V2. And what do you think about the charge? So let's imagine that this capacitor is holding a charge of Q1 and this capacitor is holding a charge of Q2. What do we think the total charge is as one large capacitor? Yeah, no, not this. What happens is, when capacitors are in series, their charges are always equal. So Q1 must equal Q2, and not only that, but the total charge of the two capacitors combined is the same as the charge on each capacitor. Now, the reason for this, Zach, is exactly the thing you copped earlier about how when they're in series, one feeds into the other. You have this effect where there's a cancellation in the middle, so it really only matters what's happening at the end plates.
It makes it like one big capacitor.
Yeah, with internal actions that aren't important. Kurt, this is constant. Do you get that? Yeah? Dorian, you have that? So look, there definitely isn't time to do this one example, and this is the only example I have, but it's a long one. So what I would like, I want you to finish the IV from earlier, and your homework is, I would like you to try this yourself. Okay? Can you take a picture or whatever you like? Yeah, or just get it from the video is fine. Be nice to Lynn, okay? Right, what's for lunch now? Uber Eats? You have your lunch today? Gina, you have your lunch? You've no lunch? Do you have lunch? Lynn?
haven't decided yet.
Undecided. No. Black. Harry? Got lunch?
Yes, but I'm sitting in one minute.
Are you thinking about it?